welcome to the stage Dr. Linda Chrisey.
Hi, everybody. I'm glad to be the cleanup hitter, I guess, for the conference with this last panel, Hardening Supply Networks for the Future. I am a program officer in the Biological Technologies Office, and I'm really pleased to be here for this discussion. Before we get on to bringing out our panelists, I just wanted to explain my moderation of this panel. You heard from Dr. Jordan a couple of sessions ago about all the fascinating programs BTO is doing sort of outside of the biomedical realm, and this is an area I'm really passionate about. So I manage a program called EMBER, which is looking at applying biotechnology solutions to the rare earth element separation and purification challenge that you also heard Dr. Duchak mention. So we're thinking about using biotechnology in really creative and different ways to solve these hard problems. So for the discussion today, we hope that we illustrate some of the challenges facing supply chains of various types for our country. Importantly, we hope to stimulate you as our audience to provide innovative ideas on how we can overcome some of these challenges, not just for the Department of Defense, but for the national security of our country. So we are delighted to have a terrific lineup of panelists to help us get through this topic today, and I'm pleased to introduce them to you. I'm going to start with Dr. Senthil Arul. He is an R&D program manager for the Defense Logistics Information Research and Supply Chain Management programs at the Defense Logistics Agency. Hi, Senthil. We also have with us today Dr. Carl McCants, who is a special assistant to the DARPA director, and he focuses on the Microsystem Technology Office's Electronics Resurgence Initiative, as well as the National Network for Microelectronics Research and Development. His previous experience includes the supply chain and cyber directorate of the National Counterintelligence and Security Center. We also have with us Mr. Wallace, or Wally, Patterson, who's a program manager at the Air Force Research Lab Materials and Manufacturing Directorate. Wally has over 36 years of experience as a civilian in the Department of the Air Force R&D acquisition system. So before we get into the discussion with our panelists, I'd like to briefly introduce you to some of the factors that can affect our supply chains. So as consumers, we're probably really accustomed to like walking into a supermarket and picking up something off a shelf or ordering it on Amazon. But before that product reaches the point of distribution we can buy it, a whole bunch of things have to happen. And so this slide is meant to show, with simple icons, the large and complex number of factors that actually go into producing a product. So as you can see, and any one of these can produce vulnerabilities for the supply chains. So for example, a production facility, the operations may go down because of a contamination problem, availability of trained people, raw materials or feedstocks, which may come from different parts of the world, equipment needed to make the product. And then importantly, as you heard from some of the previous speakers, transportation networks to move the raw materials to production facilities and then those finished products to consumers where we can buy them in the supermarket. And of course, economics, security, and then what's happening around the world can also influence these supply chains. So without focusing on any specific product, this image is meant to illustrate what I just explained, the level of complexity involved in producing a product. So for example, something you buy in the supermarket may originate with raw materials that come from many continents that go into the intermediate products, and then finally the finished products that you would buy. Transportation of these intermediates and those finished products have to be executed, seamlessly. And disruption can occur at any of these points. So a couple of examples, just to, again, make sure everybody's kind of on the same page with what we're talking about. I'm sure many of you are familiar with these recent examples, including one that was mentioned a little earlier that related to infant formula. So this was a very emotionally charged disruption. People were unable to purchase infant formula in supermarkets. And it was not until the United States was able to reach out to international partners to get supplies of that infant formula brought to the country. And then, of course, there were distribution problems in actually getting that baby formula across the country. So it is one that, again, was resolved, but it was one that was, I think everybody clearly remembers. And then several people have mentioned the pandemic. and the challenges that that has presented. This is probably a very familiar example. Early on in the pandemic, access to the materials and supplies needed for diagnostic test kits, for protective gear for healthcare workers, and protect other people from getting infected, ventilators to keep people alive, oxygen to keep people alive, those critically ill patients. All of these were, very emotionally charged and obvious challenges. So those challenges are continuing today. We hear about pilot shortages, people who are ill, who can't report to work, truckers across the country. So there are sort of enduring effects of the pandemic that we're going to hopefully learn from and be better prepared. So hopefully this very brief overview has given you a sense for what supply chains are and the many potential sources of disruption. I'd like to turn the floor over now to our panelists for some opening thoughts. And we're going to start with Wally Patterson. He's going to describe the various elements and weaknesses of a supply chain and how biomanufacturing may offer opportunities to harden DoD supply networks.
Thank you, Linda. Yeah, so on a daily basis, we track items of interest using smartphones, watches, a number of different electronic devices to track items of interest and monitor the health of systems that we use. When you order a product online, and I'm sure many of you have ordered products online, especially during the pandemic, the company you purchase the product from sends you an email, sends you that your order's been processed and shipment has been arranged. And then if you want to track the package, you can sign up for tracking emails or text alerts on your smartphone. Sometimes the tracking website gives you the current status of the package, actually where it is in the country, a timeline for expected delivery, and I've even experienced it where they can actually show you a map of the exact location of the delivery vehicle and how many stops that vehicle has before they get to your house. When the Air Force flies a mission, the aircraft and the pilot are monitored using thousands of sensors, a myriad of displays with sensors that indicate the status and health of numerous systems and subsystems on that aircraft. When you drive a car, it's got dials, readouts, audio alerts, warning lights. Some are digital, some are analog, and some are simply trouble lights. That dashboard allows you to monitor the status and the health of your car in real time, where it is in many cases. So why would the Department of Defense be interested in biomanufacturing? Well, biomanufacturing is built on biotechnology. It's an engineering discipline that utilizes or exploits living systems of various kinds to produce a wide range of technologies and products. Future advances in biotechnology will provide new operational capabilities to the Department of Defense across multiple domains, spanning materials, systems, military medicine, warfighter performance, and chem biodefense. So some examples that you see on the chart here, we are able to produce sustainable, clean sources of multi-purpose polymers, high quality, zero allergen alternative protein powders that are actually produced in former bioethanol plants. And we can actually produce materials that are only possible through biology. That you can't do them through synthetic processes. So they produce a specific structure, a narrow size distribution, and a high chemical purity, such as the vial that you see in the inside, or the center there, is actually magnetosomes, magnetic particles that were produced using bacteria, and shows the magnetic properties where it's holding up the piece of iron there. So in the Department of the Air Force, our technology supply chain actually provide the capabilities that go into our weapons platforms. And I believe that these platforms, these systems, these supply chains need bespoke dashboards to provide program managers with actionable insights into supply chain gaps and risks. A simple check engine light won't do. But I'm specifically interested in biomanufacturing. And as you heard Dr. Juchek mention, the image on the left-hand side, it's the supply chain is not just a sequential grouping of individual companies that have relationships between each other. You can't just take domestic feedstock, throw it in a vat for fermentation, and out pops a relevant product. It's actually more complex, like the image on the right-hand side and that Dr. Dutek mentioned. It's very complex with many tiers and a variety of relationships in a supply and demand network rather than a supply chain. So my goal is to completely identify the necessary and sufficient elements of a technology supply chain, not necessarily a product supply chain, but a technology supply chain in order to manage risk, predict gaps and disruptions, and mitigate vulnerabilities before they become a problem.
Thanks, Wally. That was a great introduction to biomanufacturing. Let's move on to Dr. Carl McCants from DARPA on challenges facing a clearly DoD-relevant topic, semiconductors, and securing supply chains for microelectronics. Carl?
Thank you very much, Linda. In case you're wondering what's a nice microelectronics guy like me doing on a biomanufacturing panel, we all have the commonality of understanding what supply chains are, really what supply networks are, and the impact that they can have on every aspect of what's happening within the department. So what you currently see on the slide before you has to do with if you were like me and you like to take things apart. I had the knack as when I was a kid of taking things apart, looking to see how they worked. You'll see inside a desktop or even a laptop, if you're that bold, what look like little packages. Those are the integrated circuit chips, the semiconductors that make up the backbone of almost everything that you do today and everything that you utilize today. So what I'd like to do, go on to the next slide, is to talk about what's involved in manufacturing these semiconductors. And you'll begin to see that, just as Wally was saying, it is a complex network. So this slide basically shows that when we talk about manufacturing, it starts with an idea, it goes to design. There is an ecosystem, if you will, a supply network associated with the design of the semiconductor. There's the manufacturing. So there are the materials, the chemicals, the equipment, the IT that is involved in the manufacturing process. It then moves on to the packaging and assembly, where again, other things are involved in different set of materials that are utilized to make the packages themselves, but you're still talking about an integrated network of suppliers that feed into that part of the manufacturing process. Then we go to testing. So you have to have the test tools, the equipment, the software, the algorithms, all the things that you're doing to make sure that what you received coming out of the manufacturing process meets specifications. Then it goes to the board that you saw before, and then finally the logistics out to the various customers. So that's a quick overview, and we'll get into things a little bit more as we go on. Back to you, Linda.
Sure. So there we go. So our next speaker, Dr. Senthil Arul, is going to give us a brief introduction to some of the supply tools that DLA is developing for supply chain monitoring. Senthil.
Thanks, Linda. Good afternoon, all. I want to start with what Wally and Carl were talking about. These are vertical supply chain or vertical supply network. We talked about biomanufacturing. Carl talked about semiconductors. Prior to the break, Dr. Dutek talked about what DLA does. That's where I work in DLA R&D. Our problems are different, as Linda alluded. How does the item go from the warehouse to the ultimate customer? In our case, it could be a military need in a contested environment, or it could be an emerging situation in a humanitarian situation. So if we think in that scenario, can you stop the slide? Don't do the simulation, please. Just stop. So if you think about this particular tool I'm going to go through, it originally is one of the project transition from DARPA. So we do work with transition. What DARPA team is saying is true. This project originally started as Lagrange program within DARPA. And our director visited DARPA and saw this tool. And he told us, take this tool and customize to what DLA is. So we took the tool, which was looking at the tiered supply chain, and we modified it to say, OK, here's US warehouses, European warehouses. As Dr. Dutek mentioned, we have about 30 warehouses around the world. Now, these items, there's 8 classes of items, which include water, fuel, uniforms, medicines, and reparables. All these items need to move to the customer in a contested environment. You can think this is a virtual simulation as no real data. So if you think about what's going on in the Eastern Bloc, there are warehouses in US, in Europe, and there are customer side that we need to ship the items to. So that is what's shown here on the European side. In US side, we have warehouses. We have containerization point. That is, items come from different warehouses of many different items. We pack it in a truck to the fullest volume and then ship it to the seaport or airport. From there, depending on the urgency, the need, the priority, it'll go by the air or go by the sea and reaches Europe. And then we repack it and goes to the warehouse and then to the customer. Also, in some cases, you don't see it in the simulation. It can directly go from the manufacturer to the customer too. We have all those choices here. Again, thanks to DARPA for giving us this tool, and we have built on it. If you go to the next slide, I will try to explain what are some of the capabilities we added. So you saw the simulation was running. That capability, putting the GIS into it, we did it. So you can visually see warehouses with the circle, which if you watched it, it gets smaller and smaller. That means quantity is reducing. You've seen that, and then if the transportation goes by air, it goes faster. If it was going by ship, it was going slower. So we built that capability now. We also, using the Lagrange model, we modified a little bit to see, okay, Dr. Duchek referred to just in case and just in time. So there are two things that are there in inventory management, small s and large s. What is the minimum quantity you need to maintain? What is the maximum quantity you need to maintain? If you look at your own household, we do that, right? And then when it comes in between, you go buy, right? So the same concept there, S&S. But what happens is this S&S is business rule done many, many years ago. So all the items are, here's the minimum quantity. If it comes close to minimum, we're going to go order it. And it takes 60 days to replenish it, so make the order 60 days before. It's a pretty simple math maybe using. When you run this simulation, say next 100 days or next year demand to the customer, we can run this simulation and see how S&S changes, so we can dynamically change these things, so we don't have to have too many of these items if we don't need it, depending on the warehouse. So that's one capability we added. Hey, don't depend on whatever was given to you, dynamically change S&S. We added that capability here. Next slide, please. So other two capabilities are tied together. You probably heard the bottleneck concept, right? If a disruption happens either in the supply chain, it could be in the transportation, like what happened in Suez Canal, or it could be in a war scenario, transportation method the road got damaged, or in a hurricane situation, we need to find an alternate route. So what happens is you get a bottleneck. So this one is a simulation tool. You can think of all the things you could do to simulate, right? Once you simulate, you find the bottleneck, and then how do we solve it? Can you find an alternate location for another warehouse, temporary warehouse, or we can find a change of transportation mode, or we can find another containerization point. So those two things are tied together. These are the capabilities we added with the tool, and we'll get more into it, some of the things that we are planning to do. Thanks, Linda.
Thanks, Senthil. And thanks also to the rest of our panelists for those great introductions. Let's move on to our discussion topics before we open the floor to questions from the audience. So let's start with topic one, providing resiliency to existing supply networks. And Senthil, the simulation model that you just described and showed appears to be a pretty powerful tool for examining supply chains and identifying different issues and alternatives. Are there other approaches that provide additional resiliency to supply networks?
Absolutely, right? Firstly, thanks to DARPA, the Lagrange model, and then we improved on it. So a lot of improvements can be done. But I want to go back to the quote from George Box. All models are wrong, some are useful, right? All simulation that way, just as useful as how we make it. So the four capabilities we added, it is very useful for operational folks, but that is not enough. So if you think about it, we are in the fourth industrial revolution. That means the digital leads the physical, digital thread, digital twin, cyber physical, all those terms are there. A simulation is a static model. How do I get the static model to be more dynamic? I'm not talking about adding more probabilistic, more distribution kind of thing. I want a real world information. I think the previous panel talked about the operational environment is dynamically changing. How do I get the feedback into my simulation? Is not anymore a simulation, it's a digital twin of the physical world. Can I get the feedback either from the transportation sector or what's going on in the field, get that information, they themselves can put it in the model and see how the output changes. So that's the area we're working on, is bring the dynamism from simulation to a digital twin, putting the real world data into the model, and continue to improve the model. That one area we are working on, we believe that's, as Dr. Duchek mentioned, that's an important part to react to the operational environment.
Thanks, Senthil. I'm going to go next to Wally because I think the question of versatility of raw materials and feedstocks is another area where we might be able to provide resilience to supply networks. And I'll point out, we were really excited to see that President Biden signed an executive order 2 days ago, good timing for this meeting, really amping up the attention and investment in biomanufacturing with the rationale that it will help secure our supply chains domestically and reduce our reliance on purchasing things from foreign entities. So I'm curious to know, how do you feel about that in terms of diversification and providing resiliency based on different feedstock materials that bio may enable?
Well, it largely depends on where you get those feedstocks and how we can leverage different microbial chassis to take advantage of them. There was a recent event where a U.S. biomanufacturer created a new product, was going to make tons of it, and then they decided, okay, well, where are we going to do the fermentation? They ended up going to Brazil because that's where the feedstock was. That's where the cheap network of feedstocks are. So in order to support a robust and resilient biomanufacturing ecosystem in the United States, there are a number of things that are going to be necessary. One is characterization of multiple different types of chassis that can take advantage of the multiple types of biomass that are available in the United States, whether they're a byproduct of agriculture or a waste product. To be able to valorize those feedstocks would be very important to support a resilient bioeconomy. Having those feedstocks domestically sourced would be very important.
And by chassis, you mean the actual organism that's going to make the product?
The type of microbe, yeah. So the typical chassis that maybe all of us have some familiarity with is yeast that they make bread or beer or wine with. But we can actually take those same chassis, that same type of microbe, and program it to make other things of interest, like I mentioned the polymers and other things that actually some of them came out of the Living Foundries program at DARPA.
Excellent. Carl, do you have thoughts on how we can improve resiliency for our supply networks in that semiconductor and microelectronics area?
Certainly. I think the first thing that I would say with regard to the security really has to do with understanding the dual nature of what's required to provide security. So you have the physical side, in other words, what am I looking at with regard to how things are physically coming into the plant where things are manufactured. But more importantly is the cyber side, which is the accuracy of the information that's associated with each step in the process. Am I accurately monitoring where these wafers are? Am I accurately monitoring what my supply of chemicals and gases looks like? Am I accurately monitoring who has access to the tools and the information, more so the data that's involved with that? And so when you start looking at that, then you start thinking about, okay, what are some of the things we can actually put into place to mitigate the risks associated at each of those steps?
Thank you. All right, so let's move on to our second topic listed here, providing security to supply networks in the face of threats. So with this topic, I'd like to think about managing supply network risks from end to end. So what are some of the options for protecting supply networks from threats ranging from feedstock supplies, equipment, or workforce shortages to cyber threats? Security means a lot of different things to a lot of different people. Senthil, do you have some thoughts on what approaches are being explored in this
Thanks,
space?
Linda. I'm going to take in a narrow area of information technology and data security. It's nice to be the last panel. We could hear what all talked about yesterday afternoon and today. If you think about it, we had a session on securing cyber, and I believe it was John Launchfield talked about to win the war on cybersecurity, we need to be leading it. We should be completely remove all the vulnerabilities, right? And then later in that afternoon, I believe it was Josh Feynman from Intel said, "What cybersecurity? There's no cybersecurity at all, right?" And then the panel before this, they came and said, "Where does it start? It starts in my house." Wait a minute. I am DLA. I want to serve the military at the lowest cost for all the material. I want to bring new suppliers in. How do I convince them that, hey, we have a secure cyber? I'm looking to DARPA, help me here. I don't know what to tell to bring new suppliers. Where is the security? Is it on the other end? We're going to secure it? Or is it on the other end? There's no security. So to me, that's the very interesting thing that we really want to bring new suppliers on board. How do we go about doing it in a secure way? Either it could be real physical security or it could be virtual security, but we need to know what that is.
Thanks. And Carl, how do we define security in regard to the microelectronics and semiconductor space? What are some of the approaches being explored, and who's leading the charge for innovation?
Sure, I'll say thanks, Senthil, and thanks, Josh, for just kind of voiding all the things that I was going to say about security. Not that I'm going to make up anything, but really what you talk about when you think about security, it's addressing an active threat, if you will, or addressing what you perceive are the things that would negatively impact your ability to execute the function, the mission, whatever. So you start looking at, what do I need to deal with? How do I protect, for example, the intellectual property that I've developed? And I'll go back to my area of interest as the microelectronics guy up here. If I'm developing new ways of making the semiconductors, all right, how do I protect that? How do I protect the design? If I've got a new idea for a whiz-bang thing that will make my radar much more sensitive at a tenth of the power, how do I protect that design? So you think about the technical documentation, you think about, again, the cyber system, but I will, tag on my brother here and say, yeah, we are still looking at how do you create and define the actual metrics to measure, to determine whether or not you've reached a level of success in how well you protect things. We're familiar with what's called the zero trust approach. NIST has a standard about that, where you're looking at how you actually protect data, how you protect information, how you deal with the people. It's putting the right kernels, if you will, around those pieces. But ultimately, it still comes down to the humans and how you modify that policy according to the nature of the threats that you have to mitigate.
And then in some cases, there are even trusted foundries where if you really want to have control of your process, you want to keep it in-house.
Yes, Linda, and that is about another hour discussion. That if anybody wants to talk to me about that afterwards, we can definitely do that.
So I'm just curious, because we have folks who are interested in bio and microelectronics and then general supply chain challenges. Are there other definitions of security that we haven't addressed yet in our conversation? Like maybe different suppliers or multiple suppliers where possible for ingredients, feedstock, intermediates. Is that a strategy that's sort of universally adopted across industries? Do we need to do more of that?
Let me jump in with a little bit more from semiconductors, because one of the things that's important when you start talking about security, it's recognizing and the importance of being on the same page with each supplier in your network of suppliers, that there's a common understanding when, company A talks about security and company A has, N levels of suppliers to that. That there's a consistency in the communication of these are our policies, so the policies down here have to be consistent with that. So in each part, as they're supplying and providing into that, there is that ability to view what's happening in the accuracy and the veracity of the data that's associated with the material movement as we move forward.
I think it also depends a lot on what you mean by security. So if you're securing a supply chain, is it really not so much about security, but the assurance that those supplies, those materials, those capabilities will be available when you need them? So security and assurance, I think, may be two different things.
Equally important.
Yes.
Linda, one thing I could add is you may want to go a level above security, right? It's about resilience, right? And also the previous panel talked about resilience of supply chain or resilience of the soldier. So we had to start with the resilience of the soldier. We want to make sure he can execute his mission without a hitch. So we need to take the resilience soldier, and we need to look at the resilience of supply chain. I think a lot of the work DARPA is doing, I'm so excited, biomanufacturing, it completely changes. I think some of the Directorate talked about some of the projects, waste to food. So we don't need to wait for a whole new supply chain to come as Dr. Duchek challenged us. We need to rethink, right? I think you need to change it to more resilient way of thinking.
So yeah, distributed manufacturing, if you could provide things where you actually produce your material of interest on site, then it changes the way you do logistics. It changes your calculus about the whole thing. It changes your risk signature in terms of how many people do you need to move all this stuff. The question is can you source the materials you need at that local place? So basically you eliminate the need for a heavy logistics tail in that. One of the quotes I've heard is amateur study tactics, but professional study logistics.
Yes.
And so we've got professionals right here.
We've heard it a few
I
times.
think I can just add to that is Gary Shields from Carter Rock from Navy. He says our thought should be innovation at the speed of fight. Take the thing to the field rather than think about all the supply chain. We got to produce right there with the material we have.
Right.
So somebody, maybe it was Wally, mentioned the difference between assurance and security, but there may also be a little confusion on how we define risk versus resiliency. Any comments on that? What are the differences between preventing or assessing risks and preventing risks and being more resilient? What's the connection there?
So I'll start and then defer to my colleagues. I'll look at this from a kind of a counterintelligence perspective. You look at risk as a function of threat, vulnerability, and consequence. And so a threat is specific and credible information that something's going to be targeted by unauthorized personnel or an adversary. A vulnerability is a weakness that is either inherent in that system or product or has been introduced. The tack in your bicycle tires you're writing down, that's an introduced vulnerability. So when we talk about supply chain risk, it basically says the capability and or intent of an adversary, the unauthorized person, meets and aligns with the opportunity to exploit a vulnerability. Resilience, on the other hand, really has to do with the ability or capacity to absorb and recover functionality after that shock and the ability to thrive in that altered circumstance. So if you have resilience in your supply chain, typically three things happen. Number one, the immediate impact of that shock is lower. Second, the speed of recovery can be faster. And third, the extent of the recovery can be higher because you've learned from the things that have happened. You've understood what it takes to modify the aspects of your supply network to prepare for the next one so that when things happen, you're basically going to a higher level than where you were before because now you're armed with more information than before.
No, that's fantastic. So I want to make sure we don't run out of time before we get to our last question, which is preparing for supply network instability. Thoughts on that? I mean, so we've learned a lot from the pandemic, and we heard many examples of supply chain challenges. How can we do a better job? What tools do we need to develop? Are there other innovations we need to be bringing into this subject area?
So I think one example is tools that are being developed. There's actually a solicitation on the street right now from the Defense Innovation Unit that we heard about earlier today. It's a project called Argo Navis, and it's actually the solicitations are due on Friday, but they're looking at supply chains and not necessarily the relationships between companies, because we have a lot of different tools out there that can do illuminations of supply chains that track how companies relate to each other. But the Argo Navis is specifically looking at using artificial intelligence to illuminate supply chains in terms of the actual materials, the pieces and parts. What are the things that when they're missing, our supply chains don't work. Our products cannot be produced. The microelectronics cannot be manufactured. Things that may include rare earths or something like that. So the idea would be this is a generic tool that would be able to look at any particular supply chain and just pick a product that you can think of and be able to identify that and then say, okay, what are all the things that go into making that? What are the materials? What's the equipment? And then what are the materials and processes that go into making that equipment? Basically blowing out the entire supply chain and then being able to identify some gaps, some vulnerabilities. So if we find a particular material that is no longer available in the United States, what are we going to do? Do we have another way, just like Senthil's tools? What are the alternatives? What can we do to mitigate that and predict that in the future?
So other thoughts on how we can better prepare?
So Linda, here my thought a little bit different from what Wally is saying. The models are good, they work, but there are two issues. The first issue I would say is, if you read any recently published papers with all the supply chain issues going on, and they talk about two things. What causes supply chain disruption? Hey, we all know that. It's man-made or natural disaster. So we know the causal factor very well. What causes it? How do we fix it? We know that too. Proactively fix it or reactively fix it. We know that too. Then what is the issue with supply chain? Two important things that I noticed is vertical supply chains like biomanufacturing or microchips. It's private companies. It's confidential information of their supply chain. We can't get the data, right? So if we ask for it, we don't get it. In fact, I think in October, the White House publishing the manufacturing strategy, advanced manufacturing strategy. They have 3 goals. First one is the manufacturing itself, advanced manufacturing. Second one is the workforce. Third one is supply chain resilience. One of the things they are asking is how do we get the supply chain visibility? What research we need to do? Because we really cannot go and ask Boeing to share your supply chain information with me because I can talk to Lockheed about it, right? So that's one big issue of this vertical supply chain or horizontal supply chain like microchip. We have that issue. Second biggest issue is MXU, one of the Manufacturing Innovation Institute published. I mean, I'll be right with exact numbers. 80% of the U.S. manufacturers are smaller, mid-sized manufacturers with 10 to 40 employees. So they are not on Industry 4.0. That means their model is not digitally to physical. So in order for you to illuminate the supply chain and get the data, we need to get them on Industry 4.0. How, again, that comes to cybersecurity. All the data shows is a mom and pop owned stores. They are afraid to go digital because anything happens and DLA catches them, hey, your vulnerability, they say they got to go out of business. So those are the 2 areas. One, how do you get the vertical supply chain illumination? How do you get the bottom 80% of the small and mid-sized manufacturers into the digital world? Those are 2 things I would say important.
Thank you. And not to give you short shrift, Carl, I'd like to see if there are questions from the audience, because we only have a few minutes left from the session. Okay, so what supply chains are adaptable to provide more resiliency?
My kind of standard answer is
big
any
question.
supply chain could be adaptable if you've got the time and the budget to do so. So in terms of resiliency, many cases you're going to have to pay for it. A lot of times when we would design something, we don't design an alternative for everything. We don't have necessarily an alternative material. We don't have an alternative design. We kind of stick with one thing. But if you want to start to look at, we have 3 different materials that we could use, or we have 4 different designs we can use, somebody's going to have to pay for that. So to a certain extent, it's the will to do it, and budget, as well as the time.
It seems like that presents some dynamic tension because you want things to be more secure, but what cost are you willing to pay to have it be more secure?
Yes.
So we have another question. Is there an inherent trade-off between supply chain resilience and the level of exquisite performance we currently enjoy in our end products or systems? Or can we have both? Who would like to take this
I'm
one?
looking at Carl.
So I would first proffer that it's not necessarily an either or. I believe you can have both in terms of having the resilience of the supply chain and the performance that and I'm going to make an assumption that it's referring to the performance of the product or service that's being acquired. And so there is a way to have the resilience. I think the challenge comes in when you start looking at some of the more exquisite products. And I'll give an example. If you think about your mobile phone, you have to ask, okay, well, who makes the glass? Primarily, it's going to be Corning, or maybe one other supplier. Are there other people that can make the glass that has the properties that are necessary for you to keep that phone for more than 3 months with the pounding and the dropping and everything else? So, what's the resilience in terms of the supplier of the glass? Same thing with the components that go inside the phone itself, the case itself. Where is it actually put together? If there are issues with regard to the employment at the plant that's over in China that is actually assembling your iPhones and other components, how do you deal with that? So I think there are ways to do both, but as Wally mentioned, it really comes down to, are we willing to pay the price that's necessary to improve the resilience without completely negatively impacting the price that we've grown accustomed to. We've grown accustomed to inexpensive products that have incredible performance. And so at some point we have to start asking ourselves, are we willing to pay a little bit more because the suppliers are now ensuring that the shock that we saw a couple of years ago does not repeat itself, or if it does, that the impact to the consumer is minimized.
Do you have any thoughts on this one, Senthil?
And I can add a little bit to it in the sense, can we have both? I don't want to say don't need both. Yes, we need, if we can get it at the lowest cost, yes. So if we ask the other question, supply chain resilience, as Wally alluded to and earlier session alluded to, is to challenge the supply chain, what we need is make it where you need it, when you need it. If we can get to that paradigm, if I can sacrifice some of the performance, I'll go for it, because I can produce it whenever I need it. So it performs 1 mission, 2 missions is enough, not 50 missions, something sitting there for 50 years. So I think there is a trade-off spaces there, especially with the digital manufacturing coming on board with additive, where we can push the technical data to make the part right on the spot. Should I need all the performance requirements of a subtractive manufacturing? I don't think so, because you can make the part in a much shorter period of time. So it's something to think about.
So we have another question, maybe related to one of the early ones. What are the challenges in hardening supply chains for traditional manufacturing versus agile or modular manufacturing, such as biomanufacturing or maybe even additive manufacturing? Are they different? Or is it a sort of common set of new practices or practices we have to be willing to pay for to solve the problems across these different paradigms?
Here, looking at you, Wally.
I'm considering this. I'm looking at the agile and the modular. So one of the things that any type of manufacturing facility is plagued with, to a certain extent, is that facility is built in order to produce a particular product. Okay, in order to make it agile, you have to design a lot of flexibility into those systems. So the systems that are actually going to produce what you're going to make. So we kind of come back a little bit to the chassis kind of idea. If I can build an agile biomanufacturing facility that can make a number of different products using a number of different chassis, I'm not sure that hardening it is going to be much different than a traditional supply chain, in that you're kind of going back to what Carl's saying, you're protecting the intellectual property, you're protecting the data networks, you're protecting, to a certain extent, the people as well, because that's where a lot of the intellectual property lies. So I think it's more challenging for modular manufacturing because there's a lot more technology involved. Whereas traditional supply chains, if they're sequential, tend to be simpler. So I think in some cases the biomanufacturing, agile and modular, are more complex. So to a certain extent, the complexity of the protection changes.
Now, I might add, so we talked a little bit about distributed manufacturing, and one challenge might be with the workforce. Are you going to have the workforce you need if you now don't have that centralized facility near a big city, for example? Getting the right people with the right skills in the right place to make the right products. So it seems like there may be some trade-offs with these different options.
In many of our manufacturing innovation institutes, education and workforce development is a primary key. I mean, in terms of the types of programs that they fund. At the annual Defense Manufacturing Conference last year, one of the topics that came up over and over again was skilled technicians. Yeah, PhDs are great, and we need those, but we need more skilled technicians basically at the shop floor level.
The entry level.
And that includes in biomanufacturing as well.
So we're at the end of our time. I just want to thank our panelists for this great discussion. I want to thank the audience for listening and also thank the organizers at DARPA for giving us this opportunity to talk about this topic with you. So thank you.